We want to run through some examples of the types of problems that you might see on the exam, or might help you as you run through some review problems as you're studying for the exam. So in this particular problem, we've got two people, neither of whom decided to study for a test. So they're just going to answer each one of the multiple choice questions that they come across just randomly answer the questions. So our goal is to figure out the probability that both people get the same number of answers correct. So what we notice first is that we've got a binomial distribution here. We've got the trials that are identical. They're answering the same types of multiple choice questions. They all have 5 answers, and they're independent because they're guessing. The person's guessing. So we're just going to concentrate on Smith first. Jones's distribution will be identical because Jones is taking the same test and doing the same guessing. All right. So the questions are the trials. So our n's of 5. And success is answering correctly. Well, there's one choice that's correct out of the 5, so P is 0.2. So let's just run through the possible probabilities for the values for that the random variable can take on. So remember our formula for the binomial distribution is number of trials, choose x. So that's why we have 5, choose 0 here. It's P to the x. X is 0 here, so we got 0.2 to the 0. And then it's 1 minus P to the n minus x. So that's 5. The exponent should be 5, and our probability of failure here is 0.8. Calculating that, we get about 0.3277. When we can see the other ones here, calculate those quickly using the same formulas. Here's your probabilities for exactly 1 correct, exactly 2 correct, 3, 4, and 5 correct. And you could check that this really does give you the PDF. Those should add up to 1, obviously, since we have a PDF here for a binomial distribution. Okay, so these are the probabilities that Smith gets them correct. Well, those are the same as the probabilities that Jones gets those particular values, that particular number of questions correct. So, and Jones's answers are independent of Smith's answers because both of them are just guessing. So, if we want to calculate the probability that they get the same number correct, well, that means they both get 0 correct, both get 1 correct, both get 2 correct, all the way up to, or both get 5 correct. But these are independent, so I can do the probabilities of an and by multiplying them together. So I can take the probability that x is 0, multiply by the probability that y is 0. We just said that those probabilities should be the same, and then so on up the line for 1 through 5. So this should be equal to the squares of all these probabilities added together, because again, this represents x and y both being 0. This represents x and y both being 1, etc. And if you calculate that final value, you get about 0.32. So let's move on to a negative binomial example. So in this case, we have a factory manufacturing widgets, but they don't do a very good job because 10% of them are defective. So we also are assuming here that the manufacturing of one widget is independent of manufacturing any other widget, meaning that if one is defective, that has no effect on the next one being effective or any other one being defective, sorry. And then we want to calculate that the 10th widget manufactured is the second defective one. So the reason why this is a negative binomial is because we're looking for the second success, which is a defective widget in this case, occurs on the 10th trial. And we know that these trials are all identical and independent. We were told that in the problem. Since 10% of the widgets are defective, our probability of success in this case is 0.1. We'll let x represent the number of trials until we see a second defective widget. Our PDF for a negative binomial, remember again, is number of trials, or number of trials minus 1 over 2 minus 1. So this is x minus 1 over successes minus 1. So it's n minus 1 over x minus 1 over n minus 1. So we have 9 choose 1 here. We have exactly 2 successes, exactly 8 failures. That's where this part's coming from. Remember, the reason why we subtract 1 off here is because we're looking for arrangements in those first 9 trials, in this case 9 trials, where there's exactly 1 success. And then the second success has to be on the 10th trial. So that eliminates a choice that we have. And if we go through and calculate that, we get about 0.04. Here's a geometric example. We're going to roll a die over and over and over and over and over again until we see a 2. So if x is counting that number of trials until we get that first 2, what's the smallest value number of trials that we should see, so for which the probability that we're less than or equal to that number is greater than 1/2. So again, the reason why this is a geometric example is because we're rolling a die, so each roll is identical, each roll is independent, and plus in this case we're looking for the first time a tool is rolled. Remember, geometric is the first success. So in this case, since we're looking for a 2 and we're assuming we have a 6-sided die, our probability of success is 1/6. We're trying to get this cumulative probability to be greater than 1/2. So we might as well just start at x is equal to 1 and just keep increasing our x and add it on each time until we get up above 1/2. So just to do that in succession, the probability that x is 1 means you get rolled a 2 on the first roll. That means it was 1/6, which is definitely less than 1/2. Less than or equal to 2. Well, that's the probability that was on the first roll or on the second roll. To be the first 2 on the second roll, it had to be not a 2 on the first roll and a 2 on the second one. Add those 2 together, we get 1136, which is less than 1/2. So go on to the next one. Here's 1136, that's 2 or fewer rolls, which we just calculated in the previous step. Now we go for success on the first success on the third roll. 5, 6 squared, that means not a 2 on the first one, not a 2 on the second one, and then 1/6 on the end there is for a 2 on the third one, and we get 91 out of 216, still less than 1/2. So we go to the last one here. X is less than or equal to 4. Here's less than or equal to 3. Here's the first 2 on the fourth roll. Add that up, we finally get a number that's bigger than or equal to 1/2. So we must have our x is equal to 4. Let's look at a hypergeometric example. We have a box and it's got some marbles in it. Some are white, some are black. We're going to look at the number of white marbles in the selection, and we're going to select 10 of them at random without replacement. So in this case, there's exactly two types of objects we're selecting from. So we might think that this is a binomial type of thing, success and failure. However, we're selecting without replacement in this case, so the trials cannot be independent or identical in this case, so it cannot be binomial. So since we've got this without replacement part, we have to use a hypergeometric distribution. Now, the problem didn't ask for it, but we're going to go ahead and write down the PDF of this thing first. So remember, the PDF involves the total number of things you're selecting from, total number of things you're selecting, and the total number of things of each possible type. There's 10 white marbles. Those are the ones that we're interested in selecting. That's the little thing we call N1. We're selecting N total marbles. So that's our little N. There's 25 total marbles. I should say marbles and not balls. So our capital N is 25. So here's the PDF. For whatever our x is from 0 to 10, because we can only choose between 0 and 10 white balls. X of them are white, so that's 10 choose X of them. The rest of the ones that we're choosing, 10 minus X, are black, so that's why we have 15 choose 10 minus X. The total number of selections is the 25 choose 10. Now again, that's not what the problem asked for, but some of the problems you might be interested in, you might want to know what the PDF is. But now that we know these different ideas, we know that we can find the expected value and the variance, because the problem asks us to find the variance divided by the expected value. Expected value is what? It's the total number of trials, the 10, times 10 over 25, the number of white balls over the total number of balls, period. So we get 4. Then the variance is this expression. It's total number of balls you're selecting, number of white balls out of the total, number of black balls out of the total, and then this extra term on the end, which is number of total balls minus number you're selecting over number of total balls minus 1. Remember that this last term is kind of that oddball term, but these two are like your binomials, right? Remember, the binomial expected value is number of trials times probability of success, which is what this looks like. Variance is number of trials times probability of success times probability of failure, which is what this looks like. This without replacement part, this is what's changing our variance, which is why we've got this extra term on the end. But now we can calculate what we're actually asked to do. If we divide those two numbers, we will get 3/8. Let's look at a Poisson example. We've got an automobile insurer. 4/5 of the drivers that are insured are good drivers, and another fifth are bad. A good driver has the claims distributed by a Poisson distribution, represented by a Poisson distribution with a mean of 0.2, and the number of claims for a bad driver, however, has a Poisson distribution with a mean of 0.5. We're asked to calculate a conditional probability that the driver is good, given that the driver submitted one claim. Use our conditional probability formula here. Good given one claim is equal to the probability of good and one claim over the probability of one claim. Rearrange using Bayes' theorem here. So that's on top we get probability of good times the probability of one claim given that we had a good driver. And then to get one claim, either you're good and had one claim or you're bad and had one claim. So that's why we've got the sum in the denominator. Now the different pieces. Probability that a driver is good is 0.8. If the driver is good, that was a Poisson distribution with a mean of 0.2. We want exactly one claim. So exactly one claim would be e to the negative lambda, e to the negative 0.2, lambda to the first, that's where this 0.2 is coming from, divided by 1 factorial. So that's why there's not a denominator here, because we're dividing by 1. Then we have the same format in the denominator. Here's good and one claim. Here's bad and one claim. The only thing that changes really is the lambda. Those two things look identical except for the lambda. And if we calculate that, we get about 0.68. Let's look at a moment generating function example. We're given a moment generating function that represents a distribution of number of policies sold by an agent. We're asked to figure out the probability that the agent sells more than 2 policies in a day, and then figure out the standard deviation of that distribution. So remember that by definition, our moment generating function is the expected value of e to the tx. So when we do that expected value, of course, we take that e to the tx and multiply it by the PDF, add it up over the entire support. Well, looking at our moment generating function in this case, we can see that our support, look at the values for x that have been plugged into the exponents. 1t, 2t, 3t, 4t. Those values that are up there on the coefficients on the t are our support in this case. Furthermore, what gets multiplied by these e to these powers? Well, it's f of x. That means these coefficients in front of the exponential terms must be the probabilities associated with these x values. What we mean by that is that the probability that x is 1 must be 0.45. The probability that x is 2 must be 0.35, and so on down the line. In this particular problem, we're asked for the probability that x is greater than or equal to 2. Well, that means either x is 3 or x is 4, so we can add those two particular values together and get 0.2. So the probability that the agent sells more than 2 policies in a day is 0.2. The second part asks for the standard deviation. To find standard deviation, of course, we want to find the square root of the variance. To get the variance, we need to calculate the first 2 moments of x and then calculate the variance using our variance formula. So, first moment, what do? We take the derivative of the moment generating function. So, when we take the derivative, we have the chain rule, so a 2 pops out in front for the second term, 3 for the third term, 4 for the second term. That's where we're getting those coefficients. Then to find expected value of x, or the mean, we plug in 0 for t in the moment generating function. In this case, we get 1.8. To find the second moment, we take the second derivative, or the derivative of the first derivative. Doing the same process, we get this second derivative. Expected value of x squared then, as we plug 0 in to the second derivative, get those values and get 4. Now, that's not the variance. Remember, to calculate the variance, we have to do expected value of x squared minus expected value of x quantity squared. In this case, we want the standard deviation, so we're going to do the square root of the variance. So that's why we got the square root over that formula. But now if you just plug those values in, you get about 0.87 for your standard deviation. Continuous uniform example here. All right, so this one's a little bit more complicated. It looks a little bit more complicated, but it's really not that bad. All right, so we got a battery that was sold for $100. The manufacturer offers a warranty if the battery dies within 3 years. The refund is on a sliding scale. Starts out at 100 if you put in 0 for T, ends at 0 if you put in 3 for T, and then past 3 it doesn't pay anything. Apparently they're not a very good manufacturer because the battery might fail at any time between 0 and N, where N is measured in years here. So that's a uniform distribution. So it's got a little bit weird example. It's a contrived example, but makes it easier for our purposes since we know the PDF of a uniform distribution. In this case, they tell us the expected cost of the warranty is 10, and they want us to find the N. Okay, so we were told that we have a continuous uniform distribution for the time the battery fails. So if it fails on the interval from 0 to N, our PDF must be 1 over N, where our T ranges from 0 to N. Now, the expected cost of the warranty is $10. Well, if we do expected value here, typically we go from 0 to N over the entire support. But remember again that we're looking for the expected warranty. Well, this warranty doesn't pay anything past time 3. So for the expected cost, in this case, we only need to worry about integrating from 0 to 3 of the function that we want the expected value of, so the expected warranty, times the PDF. That's all we need to do. There would be, if you want to think about it, there would be an integral on the end here. It would be plus the integral from 3 to N of 0 times 1 over N, but we know that's going to be 0, so we don't need to put that on there. So this is the equation we need to solve for N, and this is pretty straightforward. We integrate 1 minus T over 3. We get T minus T squared over 6. The 100 and the 1 over N are constants, so we can pull those out in front. In fact, if we just swing that over to the other side, we'll get N over 10. If we plug in 3 for T, we get 3 minus 3 halves, or 3 halves on the left-hand side. So that gives us N has to be 15. Last example here. Let's do an exponential example. We've got a time to failure following an exponential distribution. Notice they don't give you the mean in this one, they give you the median is 4 hours. They want to calculate the probability that the component will work without failing for at least 5 hours. Had this said the mean was 4 hours, we'd automatically know that our theta in our exponential distribution is 4. However, we're given that the median is 4, not the mean, so be careful. Make sure you read the problems carefully. Remember, for the median, it's the value that the cumulative distribution function is equal to 0.5. It's the value that splits the distribution in half. Half are below, half are above. Cumulative distribution gives you the probability that you're below a certain point. So it's the value you plug in to get 0.5, so half of it's below. For an exponential distribution, we know that the CDF, the cumulative distribution function, is 1 minus e to the negative x over theta. We want the median to be 4, so we'll put 4n for x, solve for theta in this equation. So we want to solve the equation f of 4 equals 0.5, do a little bit of algebra, get e to the negative 4 over theta is 0.5, we've got to take a log and rearrange the equation to get theta is equal to 4 over natural log of 2. I'm not going to bother getting a decimal approximation because I can handle this in my calculator just fine. All right, so let's go back and answer the question they asked. We want the probability that the component will work for at least 5 hours. So that means that we want to find the probability that x is greater than 5. I'm still going to use the CDF if I can. I can do an integral. I could integrate from 5 to infinity if I want to, but I really don't want to. I've got the cumulative distribution function sitting right here in front of me. So I can rewrite this in terms of the complement, write it as 1 minus the probability that x is less than or equal to 5, which means that's 1 minus f of 5. Well, if I do 1 minus the cumulative distribution function, I just am left with this exponential piece. So the exponential piece in this case is e to the minus, x over theta in general, but for this particular problem, it's e to the minus 5 over the theta that we calculated, which is 4 over natural log of 2. And if we calculate that, we get about 0.42. Hopefully, these examples will help you with your studying for Tuesday's exam.